We now move from considerations of forces that affect the motion of an object, such as friction and drag, to those that affect an object's shape. A change in shape due to the application of a force is a deformation. Even very small forces are known to cause small deformation. For small deformation, the deformation is elastic, and the object returns to its original shape when the force is removed. The size of the deformation is proportional to the force, that is, the Hooke's law, F equals to K delta L, where delta L is the amount of deformation produced by the force F, and K is a proportionality constant. Note that this force changes with the deformation delta L, so it is not a constant. Rearranging this equation, we get delta L equals to F over K, which means the deformation is proportional to the applied force. This is only true for small deformation. As shown in this graph, the straight segment is the linear region where Hooke's law is obeyed. For larger forces, the graph is curved, but the deformation is still elastic, which means delta L will return to zero if the force is removed. Still greater force permanently deform the object until it finally fractures. We will consider three specific types of deformations: change in length, sideways shear, and changes in volume. All deformations are assumed to be small unless otherwise stated. A change in length, delta L, is produced when a force is applied to a wire rod parallel to its length L0, either stretching it or compressing it. Experiments have shown that the change in length delta L depends on only a few variables. It is proportional to the force F and the original length L0, and inversely proportional to the cross-sectional area of the wire rod A. Here, Y is a factor called elastic modulus or Young's modulus that depends on the substance. Here are some values of Young's modulus for several materials. Materials with a large Y, for example the brass or steel, are said to have a large tensile stiffness because they deform less for a given tension or compression. Young's moduli are not listed for liquids or gases because they cannot be stretched or compressed in only one dimension. The equation for change in length is traditionally rearranged and written in this form: F over A equals to Y times delta L over L0, where the ratio of force to area, F over A, is defined as stress, and the ratio of the change in length to length, delta L over L0, is defined as strain. In this form, the equation is analogous to Hooke's law, with stress analogous to force and strain analogous to deformation. Let's look at this example together. You may pause the video to read the example. The length of the upper leg bone is shortened because it feels a compression force on it. Please note that this compression force equals to the weight that the leg supported, which is 62.0 kilogram, not the total weight of the man. We use this equation to find delta L. The cross-section of the bone is A equals to pi r squared, where r is 0.02 meter. The original length of the bone is 0.4 meter. So that the change in length, delta L, is 2 times 10 to the minus 5 meter. And this is the amount of the length the bone is shortened when the person stands up. Please note, bones on the whole do not fracture due to tension or compression. Rather, they generally fracture due to sideways impact or bending, resulting in the bones shearing or snapping. On the other hand, the behavior of bones under tension and compression is important because it determines the load the bones can carry. Overweight people have a tendency toward bone damage due to sustained compressions in bone joints and tendons. Another biological example of Hooke's law occurs in tendons. Functionally, the tendon, which is the tissue connecting muscle to bone, must stretch easily at first when the force is applied, but offer a much greater restoring force for a greater strain. Unlike bones and tendons, which need to be strong as well as elastic, the arteries and lungs need to be very stretchable. The heart is also an organ with special elastic properties. Our skins are particularly elastic, especially for the young people. The elasticity of all organs reduces with age. As shown in this picture, shearing forces are applied perpendicular to the length L0 and parallel to the area A, producing a deformation delta X. Vertical forces are not shown, but it should be kept in mind that in addition to the two shearing forces F, there must be supporting forces to keep the object from rotating. Shearing deformation behaves similarly to tension and compression and can be described with similar equations. The expression for shearing deformation is this, where S is shear modulus. Here are some values of shear modulus. Shear moduli are less than Young's moduli for most materials, but bones is a remarkable exception. Its shear modulus is not only greater than its Young's modulus, but it is as large as that of steel. This is why bones are so rigid. The shear moduli for concrete and bricks are very small. That's why concrete used in buildings can withstand compression, but is very poor against shear, as might be encountered in heavy loaded floors or during earthquakes. Modern structures were made possible by the use of steel and steel-reinforced concrete. Almost by definition, liquid and gases have shear moduli near zero because they flow in response to shearing forces. An object will be compressed in all directions if inward forces are applied evenly on all its surfaces, as shown in this figure. It is relatively easy to compress gases and extremely difficult to compress liquids and solids. The reason for these different compressibilities is that atoms and molecules are separated by large empty spaces in gases, but packed closely together in liquids and solids. To compress a gas, you must force its atoms and molecules closer together. To compress liquids and solids, you must actually compress their atoms and molecules, and very strong electromagnetic forces in them oppose this compression. We can describe the compression or volume deformation of an object with this equation, where B is the bulk modulus, V0 is the original volume, and F over A is the force per unit area applied. Note that no bulk moduli are given for gases. Here are some values of the B. One practical example of bulk compression is the manufacture of industrial-grade diamonds by compressing carbon with an extremely large force per unit area. In nature, a similar process occurs deep underground. Another lateral source of large compressive forces is the pressure created by the weight of water, especially in deep parts of the ocean. Water exerts an inward force on all surfaces of a submerged object, and even on the water itself. Conversely, very large forces are created by liquids and solids when they try to expand but are constrained from doing so. This often occurs when a constrained material warmed up. Since most material expand when their temperature increases, if the material are tightly constrained, they deform or break their container. Another very common example occurs when water freezes. Water, unlike most materials, expands when it freezes, and it can easily fracture a boulder, rupture a biological cell, or crack an engine block that gets in its way.